Hi y'all. So this module is about atmospheric water. We're going to take a look at the nature of water in the atmosphere through the hydrological cycle, its formation, its function. We've talked a little bit about water and how it has great storage capacity of energy and how that energy is then transferred through the atmosphere through phase changes. We'll talk a little bit more about that in this unit as well. So most of you are really familiar with the hydrological cycle, better known as the water cycle, and you've probably learned somewhere in your K-12 education that water evaporates out of a body, such as a lake or a river, and then is transferred into a cloud mass, and that cloud mass then precipitates back onto the land, and then consequently it flows through rivers back into a lake or an ocean body. And certainly that is correct, but we're going to expand on that a little bit. So we want to think about what the vessels are, or the components that house water in this unit a little bit more concretely, and what some additional components are. So we really want to know how long water stays in a particular location, its formation in that location, and its movement through those locations. So with that hydrological cycle that you are familiar with, I'd like to add glacial ice. So sometimes that water is going to fall on a cold landscape. That cold landscape then is going to result in the retention of snow, and consequently through metamorphic action over time is going to convert that snow into an ice mass, and that ice mass can be retained for hundreds to thousands and tens of thousands of years. So the place of holding of water and storage of energy in places like Greenland and Antarctica and Patagonia become really important as localities of water storage and energy storage through glacial mass. Two other localities that aren't often included in the hydrological cycle also are aquifers, water which is housed in geologic structures, what we acquire out of wells, for instance. Different aquifers can house water for different lengths of time. So the geologic structures in Northeast Ohio have a roughly 50-year storage holding capacity. What that means is as water falls on the surface of the earth in places like Warren or Ashtabula, that water is going to percolate through the soil, penetrate into the geology, and then housed within the geology. And it takes about 50 years to do that. Naturally, it'll take about 50 years for that water to move out of that rock as well. With the inclusion of wells that people drill to access that water for various things, mostly for drinking water, we then have abbreviated that, and we're taking the water out faster than it naturally gets put in. So we don't really have a lot of equilibrium there any longer. Other locations like Hawaii, the water will fall in the afternoon on the high elevations in Hawaii. The porous nature of that rock, that volcanic rock, then allows the movement of that water through the geology over a very rapid period of time, roughly about 5 hours. And over 5 hours, then it empties out into the Pacific Ocean. The next day, it's going to rain again, and that water is going to then move through that geologic structure. So the component and the rate at which water is housed in that geologic structure is only a few hours long. Other localities like the Ogallala Aquifer in the central part of the United States, which occupies many states from the panhandle of Texas up to South Dakota, along the front ranges of the Rocky Mountains west through to parts of Kansas in the east, as is fossil water. It's been in that location and stored in that location starting around the time of Jurassic period. So millions and millions of years. Again, like with Ohio, where we've drilled wells to access that water, it takes millions of years of of time to put water into that very large aquifer, but we've extracted that water at an enormously quick rate. So the input rate is slower than the output rate for these geologic structures. Typically, without human access to that water, the input and output rates are in balance, but they're no longer in balance in large areas of the world. The third component that is not often included in high school, junior high school hydrological cycle examples is deep water in oceans, where that water can sit in situ at the bottom of the Pacific or the bottom of the Atlantic for hundreds of thousands of years as well, and then over great lengths of time will upwell to the surface and then be liberated by the warming of the earth and become evaporated. But it takes a long time for those deep ocean bodies of water to then be cycled to the top of that water channel. So each component has an input and output rates, which I've alluded to with the aquifers, the Ohio aquifers, and with the Ogallala aquifer. Other input and output rates are included in other components as well. So when we think of the atmosphere as a component of holding water, different locations are going to have different holding capacities based on what the temperature is like. If the atmosphere is expansive enough that it can hold a lot of water, it will. If it's cool and it can't, it won't hold as much. Places like low latitudes, you'll see water evaporating out all the time if there's water available, like in the mid-Atlantic or the mid-Pacific, and that water will then be transferred into a cloud structure, and then maybe within a few minutes that cloud will then precipitate that water back out. So that cycle of input and output is only minutes long. In fact, in some cases, the water never makes it to condensation to produce a cloud, and it falls back down to the surface of the earth as virga. So that can happen as well. Clouds also can be formed, and winds will push those clouds over great distances, maybe from the mid-Atlantic and then across into the high Atlantic and then across North America. And that might take weeks and weeks, in which case then that water is held in place in the atmosphere for a number of weeks as opposed to a number of minutes at those lower latitudes. So there's a lot of variability in the amount of water and the duration of that water in the atmosphere, similar to the duration of water and movement of water in those deep ocean currents, in glacial ice, and in aquifers as well. River bodies and ocean bodies, lake bodies, all have variable temporal frameworks for which that water is housed in that vessel, whether it's a river or a lake, and its movement throughout. So there's a lot of variability through each one of these components in the hydrological cycle that we need to consider.